Yeah, so GRBs are very interesting. We saw that different eras of evolution of the field and so on, and now it has become kind of a very much established field, and an internationally coordinated network is working to monitor these objects, and a very good network has been established all the way from onboard satellites and to ground-based, and it is all being done through a system called GCN. That's a GRB coordination network, and it's a big channel and link and network which has been established by the GSFC NASA, and they're working and single system through single system all the localization information being broadcasted to all possible uh, observatory and to interested people in free through this network. So one can get information in the location of such bursts from different missiles and can move their telescopes to observe such systems. Coming to the next part of the talk, that how we can understand these systems and these kind of collapse of massive star and some explosion which is coming out and liberating huge amount of energy. Talking to these, we we should be able to see first a movie where one can visualize that what's happening. For example, here is a binary, let's say binary pulsar system, binary neutron stars, somehow they are coming close to each other and gravitationally they are forced to collide, and in during the process of collision you see that it's possible that this kind of bipolar jets are coming out and which are responsible for the short duration GR. So this is one scenario which is possible. In another scenario, it's also possible that a single massive star is collapsing. Single massive star is collapsing. Here you see a massive star where surrounding dust and system is there, and if a single massive rotating star somehow, if it is becoming unstable where hydrodynamical pressure is not being able to balance by gravitational pressure, then some process might ignite the collapse and the formation of a central black hole and which is creating mass, and then bipolar jets are passing through the star and coming out through the stellar cocoon. And you see if it's coming out of the surface, it might produce a bipolar relativistic jet giving out to GRB and after. So to understand such a process, whether it's a binary collisions or a single massive star collapse, in both the situations we consider the formation of a central engine, which we actually do not know what it is, but maybe possibly a black hole or something where bipolar jets are coming out, and a very high Lorentz factor material, that's a baryon dominated or maybe magnetized outflow, is coming out with a relativistic speed with a Lorentz factor of maybe 100 to 1000, and these internal shocks are responsible for this gamma ray emission where chunks of materials are colliding with each other, giving out to gamma ray emission, where in the light curve basic spiky features and so on we saw previously. And when this matter is further deaccelerating and interacting with the interstellar matter, and when surface mass is becoming considerable amount, let's say of the order of the ejected matter, then it's possible that the matter will further deaccelerate to produce emission at lower frequencies like X-ray, optical, and radio. And that's where we are getting information. And this is known as afterglow. And this afterglow is, since it's lasting longer, it's providing more information about this mechanism than the burst itself. Because the burst itself lasts only for a few tenths of seconds. And after that, most of the information about these explosions are coming through our understanding about the afterglow properties. Next slide, please. So talking about this jetted outflow, you see that in case of a jetted outflow, it's possible that the material which is coming out with a very high Lorentz factor might produce a thermal emission in the beginning, but the internal dissipation and the prompt emission will come out as a chunks of material which is coming out from the central engine and interacting with each other. And when it further deaccelerates, forward shocks can be produced which are responsible for the afterglow. And if this material is further interacting with the interstellar matter, then it's possible that they will expand sideways, and this is further a P point where if we can pinpoint, then it will be an achromatic break can be observed at barrier frequencies at the same time, and this jet break provides a lot of information to understand about the jet opening angle and so on. Talking about the prompt emission in detail, the short time scale variability is difficult to explain as an external shock, so this order of 10 power minus 3 second of the variability can be explained and possible in form of through internal shocks only, and this prompt emission in this situation, one of the lag bursts, as you can see, and we have discussed previously, that prompt emission seen in gamma rays and is kind of very much similar, whereas the highest energy radiation in gamma rays may not come from the prompt emission because it is delayed. So this delayed origin indicates that probably some of the gamma rays, soft gamma rays are because of the prompt emission, but the much higher radiation may not be the prompt emission, but maybe of the afterglow origin, or that if at all, if it's not of the afterglow origin, then the burst spectrum is not as it was earlier, but probably it might have some other features which we do not know at the moment. And this prompt emission has also been seen at other lower frequencies also. In case of some GRBs, this gamma ray emission is temporarily correlated with the optical emission. In some of the cases it is not. In one of the very recent cases, it's called naked eye burst because it was as bright as 5 magnitude, which was able to see in a night dark sky through naked eye. And if you see in the figure, the light curve of these GRB, the black one is gamma ray and the red one is optical. They are somewhat correlated. Previously also one or two cases have been seen where prompt emission has been seen at lower frequencies like optical. So these kind of information provides a very good clue about that how the prompt emission spectrum is. If we know the nature from all the way from gamma ray to optical, it is possible to construct the spectrum and the distribution of the burst itself, which is the least known area in this field. Another important scenario in the case of GRBs is that the formation of reverse shock, where when the material is expanding relativistically, it's also possible that at some states it will interact and some kind of shock will move relativistically towards opposite direction, and that might also cause a radiation at lower frequencies like optical. And this has also further implications about our understanding about the shock physics and how the relativistic shocks are propagating through the jet. And if you see in this picture, this kind of implications might happen in case of reverse shock, where depending on the magnetization of the firewall and other properties, forward shock might dominate at some cases, whereas reverse shock is also visible in some cases. It all depends on magnetization of the firewall and the properties. Coming back to the forward shock emission, which is the most yielding scenario towards our understanding about the afterglows, is that when the metal is interacting with the interstellar media, it has been providing quite good amount of information, and its dynamics was understood back that how relativistic flow is happening by Blanchard and Mackey back in 1976. and this provides some microphysics about this outflow, and depending on what physical mechanism is, whether synchronous or inverse Compton, this area has been studied in more detail, and more observational evidences have been found towards our understanding of the afterglow.